a few take-home messages. So hydrodynamic models can be used to study many different processes occurring in fluids, ranging from short surface gravity waves in a teacup to equatorial Kelvin waves in the ocean and El Nino event. So that's the fascinating feature is that all hydrodynamic models are based on the same set of conservation principles called the Navier-Stokes equation. You can actually write the Navier-Stokes equation on one sheet of paper. These equations describe most physical processes that happen in fluids on Earth. Okay, and that's a quite fascinating feature. Why do these equations describe all processes? There are two reasons for it. One is the process that is created depends on the initial enforcing condition. So tides are created from an astronomical forcing, a so-called potential, a tide potential that creates these motions. Similarly, short and long surface gravity waves, they require some sort of wave pattern. The other reason is that the relative magnitude of terms in the Navier-Stokes equations scale depend. For example, the Coriolis force only comes into action on timescales exceeding 1 day. That's one example. And what the Coriolis force does, the main result, the Coriolis force, it turns motions to be more horizontal than vertical. This is what creates eddies, western boundary currents, these upwelling jets. So that's the fascinating bit, and thanks for tuning in. And these last lectures are only meant to be motivation. It's relatively tricky to become an experienced hydrodynamic modeler. Quite some challenges ahead, but I showed you the secrets, the most important secrets, with like how do you simulate the Coriolis. Okay, thanks for tuning in. I hope that you learned a little bit from it. Thanks.